All right. Hello, everyone. This is my submission for Lab 2. It requires that I show my face for the beginning part of the video, or I don't know, I'm going to show it throughout, but here I am. Yeah, so let's get into it. Well, this is my ALU, as you can see, in its entirety. I'm going to go through each part individually and explain it, but first I'm going to show it working with some basic commands. So at 0, 0, these two bits control my individual parts, and these last two bits here, oops, these two bits here control which component I'm working with, as denoted by this splitter right here. The last two bits go to the overall mux, control which component I am using at a single time, and these first two control how I use that component. I'll get into that later. All right, so let's start with shifting. So for shifting, A is the value I'm shifting. So it's 1, 1, 1, 1. As you can see, when it's 0, 0, I'm not shifting by any. B determines how much I shift by. So if I want to shift 1, 1, 1, 1 to the left, let's check my chart. Shift left logic would be this. And if you look, our 1, 1, 1, 1 has shifted to the left by 1. If we try it again, they're shifting to the left by 3, shifting to the left by 2, and here is shifting to the left by 4, and we go all the way up to, I believe, 16. Shifting to the left by 16. Yes, there we go. Awesome. Let's try shifting to the right by 1. Awesome. And then shifting to the right with arithmetic. So let's say I'm shifting to the right for a negative number. And awesome. So for the comparator, our comparator works by comparing A and B. And if B is larger, we have a 0 output. But if A is equal to B or A is larger, our output is 1. That's really all there is to that. All right, next we have our adder. So for the addition and subtraction component, I built that into my comparator just because my comparator uses the 32-bit adder. So for that, we denote that by this. So for addition, 1 and 1, or sorry, that's 2 and 2 is equal to 4. Yep. 3 and 2, that's equal to 5. Awesome. And if you show an overflow case, bam, overflow. Okay, next I'm going to show subtraction, which would be this. So we have A minus B, which would be 1 minus 1. If B is greater than A, then we have a negative number as a result. Signed, of course. But if we have B is too large, then we have an overflow. If we have A and then minus B, this is the result. Awesome. Next, I'm going to show the logic unit, which is our AND, OR, NOR, and XOR. It's denoted by this. So first off, we start with our AND. So this shows A and B, as you can see. Only these three are ones because only these three are ones on both A and B. Next, we're going to show A or B, like so. Now this shows A or B. Next, we're going to show A nor B, which would be this. So this is A and B. We take both of those results and we show what is not A or B. Next is A XOR B, exclusive OR, like so. So these ones right here are not showing up, but these are because they're not on both. Awesome. Now, let's get into how each individual component works, starting with the shifter. So for my shifter, we have our operation. This is at 0, it does not shift anything. At 0, 1, we're shifting left logically. At 1, 0, we're shifting right logically. And at 1, 1, we're shifting right arithmetic. Shifting right arithmetic is for signed numbers. How this works. A, this is our input, is passed into our first set of shifters, and this is for 1 bit. Now, as you can see, this is made by a splitter. We split all the pins into the 32 bits, and we just have it offset by 1. And the new bit is grounded for shift left logic and shift right logic. But shift right arithmetic has this pin right here going here, because if this is a signed number, pin 31 would be high, and so we would need to replace any new inputs with a 1 as well. For example, show an example, we have a negative number, and we're going to shift by 1. So as you can see, our new number is inputting a 1 here. Instead, if it was not a negative, it'd be inputting a 0, like so, because this number is not high. So that's the 1 bit. The way we choose what we're doing and how we're doing it is with this right here. So for the 1 bit, we go into this line here. If we follow this line, it goes into this AND. This AND right here also goes into our control for our operation. And this goes into our mux to choose what we do. Now this mux chooses one of 4 options depending on the input. So this is 1, 1, so it's choosing 0, 1, 2, and 3. It's choosing the 3rd option. Now, this AND only activates if our bit for the amount we're shifting by is activated. And then this mux is passed into our 2-bit right here. Same thing, mux is controlled by the 2nd bit here. And the reason it's 2 is because if it wasn't 2, I wouldn't be able to AND it with this line here. So I just make it 2 of itself. This also means that if I had a 0, 1, then a 0, 1 would be passed into here. But for the 2-bit, the 0, 0 would be passed through. And I just have all of these things linking into each other for pass-through. So here is the 4-bit. See how it's offset by 4? This is my ground. Here's the AND. Here's the 8-bit, offset by 8. Shift left logic, shift right logic, shift right arithmetic. And here's the 16. No need to go past 16, because if we do, then, we only have 32 digits, and we only really need to shift 31 times, because if we shift 32 times, we don't have any number anymore. So that's how the shifter works. Next, we're going to go to the comparator and adder. I combined these two because they both used a 32-bit adder from the previous lab, lab 1. So here is my 32-bit adder. For addition and subtraction, the addition and subtraction is controlled by this pin right here. And this is my sum, and I have the overflow pass through. Now, for the comparator works by checking the overflow and the carry out pins and XORing them to the comparison. Now, we compare by subtracting. So we have A and we subtract B to compare. And if our carry out and overflow are high, then A is either greater than or equal to B. For example, if this is a negative number here, A would be greater, because that's a negative. Say a negative 2. And if A were 1, A would be high. A were 5, and that was 2. A would be greater, but if this was, let's see, that is 5, 6, then B would be greater. Next is the logic unit. And the logic unit is pretty simple. See if I can't find it real quick. Logic unit. Here we go. For the logic unit, we have our 32-bit inputs going into each portion, one into each logic gate. And then our selector controls which one we choose. And yeah, that's pretty much it. So if this is 0, 0, we're doing AND. If this is 0, 1, we're doing an OR. If this is 1, 0, we're doing a not OR. And if this is 1, 1, we're doing an XOR. Now, for the chronogram timing analysis, which I have running in main. All this is doing here is saying, hey, I have 4 operations to do, and I'm just going to set them up automatically with a clock. So to do this, I had to make an incrementer to increment from 0 to 4 for these ROMs, and that is made by 2 JK flip-flops, like so. And if I just click it once, we're on 0, 1, click it again, 1, 0, click it again, 1, 1, click it again, 0, 0, like so. That's how that works. All right, so for this part, I was struggling to get the system clock working. It crashed on me a couple times, but fiddling with it enough, I eventually figured it out. You're seeing me eventually figure it out right here. Yeah, so I wasn't talking. This is my timing diagram required for the lab. I'll flash that on the screen real quick. And yeah, I just basically have to show it working automatically for these test values I inputted. And the values I chose were based on the examples in the PDF for the lab. Well, that's not really working. Turn that off, try again. Well, that's odd. It's on the second option. If I do this and I do auto tick enabled, there we go. Now it's cycling through. There we go. So we can see it cycling through our instructions. And for our 0th cycle, first cycle right here, our cycle is 0, and our command is to add A and B. So we're adding 3 and 5 together. That's what these are. If I can extend this, there we go. 3 and 5. Should get 8, but that's not right. Here we go. This is better. Adding 3 and 5. Bam, we get 8. Then we are doing subtracting 5 and 7. So subtracting 5 and 7, and we get F, 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 E, which is a negative 2, I think. It would make sense, negative 2. Then we go to an AND. So we're ANDing this number and this number, and if you see this, you should get 0 as an AND, which makes sense. And then for our final thing, we are shifting left logically by 2. So shifting left that number by 2, and we get 4. So that moves over 1, 2, that's the 4. Awesome. And yeah, this will just run. See the timing for what instruction it's on. A, B, result, and our overflow signals. This triggers every 4 seconds. All right, thanks for watching. This is my Lab 2 submission video and my explanation for how everything works. See ya.